Swayam Prabha. Digital India. Educated India.
So today we will look at a different kind of a solution to the extended Graetz problem. So the original Graetz problem was done, as I said, for the case of a plug flow with a constant wall temperature, and that was extended later by cellars to a parabolic velocity profile, and we also saw the solution to that. So now we will quickly visit the last of the extensions, that is with a constant wall flux boundary condition. Okay. So we'll look at the extended So this is of course the Graetz problem for the thermally developing region. For the constant wall flux boundary condition, either it can be with a plug flow velocity profile or a parabolic flow velocity profile. If you take the case of for example a plug flow kind of a velocity profile, you start with your energy equation, u dt by dx is equal to alpha into 1 by r into d by dr of r dt by dr. Okay. So so this is your basic energy equation. Let us what we will do here is we will not try to non-dimensionalize the temperature, because we have a constant wall flux condition, and therefore any attempt to kind of define a non-dimensional temperature will be futile, because if you define your theta something like T minus T wall by Ti minus T wall, so there it was useful when you had a constant wall temperature. Okay, so you could take this out of the differential and it will cancel off, but in this case your wall temperature is a function of x, so therefore you cannot define your non-dimensional temperature this way, so it is better to keep it in the dimensional form. Okay, and then try to solve. So what we will do, however, is to non-dimensionalize the coordinates for x and r. Okay, so we will write that in terms of zeta, and so we will define zeta as x by r naught divided by Peclet number, and my non-dimensional r is eta, which is r by r naught. So if you substitute this into the given equation, energy equation, so you get u dt by d zeta. So from here you can write your x as xi zeta into r naught into Peclet number. Now Peclet number is nothing but rho into um into d by, or you can say um d by alpha. Okay, so this I can substitute in place of x, so this becomes r naught um d, and the alpha goes to the numerator here, so this is equal to alpha 1 by eta into d by d eta into eta dt by d eta. Of course the r naught here and here cancel, so I have a r naught square which I have to multiply it outside, so my alpha cancels here, and I can also cancel off my r naught, so this I can write as 2 times r naught, so this becomes r naught square, which also cancels off, and therefore I get u by um into 1 by 2 dt by d zeta, which is equal to 1 by eta d by d eta into dt by d eta. Okay. Now comes the velocity profile which you want to use. If you want to use a fully developed parabolic velocity profile, then you substitute for the appropriate relation. So you know that u by, what is the fully developed profile? U by um is equal to twice 1 minus eta square in terms of the non-dimensional coordinate. So directly you can substitute for u by twice um directly as 1 minus eta square here, if you want to go for a parabolic flow. Okay. However, if you want to go with the classical, how Graetz started with a plug flow, then you can say that your u is equal to um. So this is for a parabolic profile, and this is your plug flow or slug flow, whatever you want to. So therefore, let us assume for the time being that yours is a plug flow. So substituting this, you get dt by d zeta is equal to twice of 1 by eta into d by d eta dt by d eta. Okay, so this is how your energy equation can be written, and now we have to state the boundary conditions. Okay, so now if you substitute the parabolic flow, you have 1 minus eta square here. Okay, 2 cancels off, you have 1 minus eta square. So till here it's fine. So now we have to state the boundary conditions for the constant wall flux case. Okay, so T corresponding to zeta equal to 0 and any value of eta. Ti, and coming to the boundary conditions with respect to eta, here you have a constant wall flux at r equal to r naught. So therefore you should rather write dt by dr or dt by d eta at eta equal to 1 is equal to q of wall by k. This is your condition. Okay, so this is your wall flux, which is k dt by dr at eta r equal to r naught, which is basically dt by d eta at eta equal to 1. So this is a constant. And what is the other boundary condition? At eta equal to 0, t should be finite, or dt by d eta at eta equal to 0 should be 0. So this implies symmetry in the profile. Okay, or this also is equivalent to saying t at eta equal to 0 should be finite. Okay, so now you see the problem. So you want to define an eigenvalue problem here. However, the direction of the eigenvalue problem, you have a non-homogeneous boundary condition. So therefore the question is, how will you convert this into a eigenvalue problem? Okay, so here is where we introduce a particular technique to do that. I have posted the solution for a constant wall flux, but in a Cartesian coordinate, that is for a channel flow on the Moodle. I have worked out the solution and I have posted it. You can just go through it, and a very similar treatment has to be done for the pipe flow case also. Just I will give you the overview. I think after that you can go through the document, and it's a very straightforward process. Okay, so what I am going to do is, I am going to now introduce theta here, which is of course not non-dimensional, but I will say this as t minus ti. Okay, so therefore I can replace this, since ti is a constant. Okay, that is the inlet temperature, so I can replace this t with theta, and the condition here becomes at zeta equal to 1, zeta equal to 0, theta will be 1, 0, t will become ti. Okay, so that is the advantage. So what I am trying to do is, wherever possible I can introduce zeros, I am doing it, and then this will be in terms of theta, this will also be in terms of theta. Anyway, Ti is a constant, so if you differentiate it, doesn't matter. Now I am going to assume that theta of x comma y can be written as independent solutions, or sorry, here it is x comma or zeta comma eta can be written as some capital X which is a function of zeta plus phi which is a function of only eta plus a perturbation which is a function of both zeta and eta. So see, now this assumption works well because this is a linear operator, the equation is linear, and therefore if you assume a linear combination of solutions, that should also be a solution. Okay, so you are assuming that your actual solution consists of summation of two independent solutions, one which is only a function of zeta, the other which is only a function of eta, and of course this is just an assumption. On top of it, the actual solution can be obtained if you have a perturbation to this, and that perturbation is, you call it as xi, which is of course the perturbation has to be a function of eta and zeta. So that brings out the interaction between the eta and zeta terms. Okay, whereas this purely talks about an ordinary differential equation separately and ordinary differential equation separately, and this is a mixed solution. Okay, so this is basically independent solutions in terms of eta and zeta, and this is the perturbation to the independent solutions. And since the partial differential equation is linear and the solution is a linear superposition of all the solutions, still this will be a solution to the governing equation. So now you see the advantage. So once you substitute this into the governing equation, okay, so you can write this as you can separate this into two problems, one where you first look at only the independent solution, and the other where you look at the perturbation solution to the perturbation, and then finally add everything together. So first part will be the solution to independent variables. Okay, so first what I say is that I have a problem. Now I can substitute x of xi and phi of eta separately, and it will satisfy this such a way that you should have dx by d zeta equal to twice 1 by eta into d by d eta into eta phi d phi by d eta. Okay, so you first assume that your independent variables satisfy this governing equation, so you write in terms of the independent variables, so you get this as terms of x, this in terms of phi, and these two can be equal if only they are equal to some constant. Okay, so then you can find this is a ordinary differential equation, this is a ordinary differential equation, this is a first order, second order ODE. Directly you can integrate and write the solutions for phi and x. Okay, so therefore you have two independent solutions, and the boundary conditions for this particular problem, in terms of x you assume that x corresponding to zeta equal to 0 is equal to 0. Okay, and corresponding to phi you assume that your d phi by d eta at eta equal to 1 is equal to q all by k, and the other boundary condition is your d phi by d eta at eta equal to 0 is equal to 0. Okay, so you apply these two boundary conditions to this. Now you get the point why I have written it that way. So once the non-homogeneous boundary condition goes to this, the remaining part, which is the perturbation, will have a homogeneous boundary condition. Okay, because once I have found the solutions to the independent variables, the solution with respect to phi will take the non-homogeneous boundary condition. Now therefore the second part will be the solution to the perturbation. The second part will be solution to the perturbation here. So if I write the equation for the perturbation, I can just give the boundary conditions. So the boundary conditions for, say, can be written as theta minus x minus phi of eta. Okay, so now corresponding to this fact, of course, when I look at d psi by d eta at eta equal to 1. Okay, so this will be d theta by d eta at eta equal to 1 minus d phi by d eta at eta equal to 1. So both will cancel off. So therefore this will be 0, because your d theta by d eta is what? Q wall by k, and also d phi by d eta at eta equal to 1, you have forced it to be q wall by k. So therefore the boundary condition, one of them becomes 0 directly, and the other boundary condition d psi by d eta at eta equal to 0, anyway both are 0, so that will also be 0. Okay, so now you see that you have reduced your non-homogeneous boundary conditions to you are now solving actually for the perturbation, which has now homogeneous boundary conditions, and now this perturbation psi can again be solved by separation of variables. Okay, so now you can say that I can assume that my psi zeta comma eta is actually some x of zeta and some y of eta, and then I can proceed with my I can now proceed with my regular solution. Okay, so what is the remaining boundary condition? That is at x at zeta equal to 0. So therefore at zeta equal to 0, your psi at zeta equal to 0 comma eta will be theta at zeta equal to 0, which is 0, minus x of 0, which is again 0, minus you have phi of eta. So therefore the boundary condition at eta equal to 0 becomes minus phi of eta. Okay, so these are the boundary conditions. So you have the boundary condition at psi equal to 0, then with respect to eta you have two homogeneous boundary conditions. So therefore if you substitute into this, you separate the variables, so in terms of y you will get the eigenvalue problem. Okay, so and that will have two homogeneous boundary conditions. So, okay, any guess what the eigenvalue problem will be here? Will that be a Bessel equation? It will be a Bessel equation, and you already know the solution to Bessel equations. You have to just combine the Bessel solutions, and then now the only difference between this and the constant wall temperature case, there the temperature was 0 at r equal to r naught. Here you have both gradient 0 boundary conditions. Okay, so this is the difference. And after that the solution is straightforward. So this is an independent solution that you will get from separation of variables, and you already have the solution for x and phi, which is a straightforward PD to integrate, and then finally you superpose all the 3 solutions and you get the final solution for theta. Okay, so this procedure I have very clearly illustrated in that example for Cartesian coordinate system. You please go through that, and in the assignment I will ask you to do the parallel thing for the duct flow also. Okay, so only thing there you have cosine and sine, here you will be getting in terms of Bessel functions. So the final solution that comes out, it was done by Sellars, and Sellars did both the case of the case where you have a plug flow as well as the case where you have a parabolic flow. In the case of parabolic flow you have 1 minus eta square which is coming here. Okay, when you substitute for the velocity profile you have 1 minus eta square and there is no 2 here, and therefore the eigenvalue problem in this case will be what? Sturm-Liouville. Okay, the Sturm-Liouville kind of a problem. So Sellars did this, and the final solution for Nusselt number (11/48) plus okay, so this r prime here is basically the gradient of the eigenfunction, which is basically the eigenfunction comes from the solution of the Sturm-Liouville problem. Okay, and these are coefficients for different values of n. Okay, so this is beta n. Now he tabulated the values of beta n and r prime beta n. So this is the case for parabolic velocity profile. So this is the solution by Sellars et al. Okay, so for different values of n, beta n square minus r prime minus beta n square. Okay, so n 1, 2, 3, the values go as 25.639, 84.624 and 176.4, 8.854 minus 3, 2.062. Okay, so therefore this is what he has done. Now you can check for large values of zeta. Okay, so nu large values, from this table you substitute and calculate what should be the nu for large values of zeta. So if you assume large values of zeta, you can say that this is an exponentially decaying function, goes to 0, the entire term will be very small, it will be simply 48/11, which is exactly 4.364. Just check that. That come to 4.364. Anyone has a calculator can? Okay. So what was so do you remember this number? This was the case there where we proved very first for a fully developed both hydrodynamically and thermally and for a constant wall flux condition. This was the Nusselt number. So now this is coming as an asymptotic solution to the Sellars solution. Okay. Okay. So these are the things, and of course the Sellars also did a case with where he did a constant linear temperature wall temperature variation. Okay, so he did all the three. So he looked at the parabolic velocity profile, and he looked at constant wall flux condition and also linear variation in the wall temperature, and he has also given the solution. I am not going to give that, otherwise it becomes too many correlations. So he has done all the three. So I am just going to plot the variation of the local Nusselt number with all the three different boundary conditions. as a function of x by r naught by Peclet number, or x by, you can plot it as d naught, which is 1 by Graetz number. Okay, so okay, so he has done for 3 different boundary conditions: constant wall flux and linear wall temperature variation, which was something like T wall is Ti plus some zeta, constant times zeta. This was the linear wall temperature variation, and of course your constant wall temperature. So now I have marked here 1, 2, 3. So you have to tell me which one corresponds to 1. Okay, let us start with 3. Out of these 3, which one do you think will be corresponding to number 3? Which boundary condition? T wall is constant. So that is number 3. So between 1 and 2. What could be number 1? Huh? Q wall is constant. How about linear variation of wall temperature? Okay, so finally, whether it is linear variation of wall temperature or Q wall is a constant, once it becomes both thermally and hydrodynamically fully developed, they reach the same value. Okay, that's why these two merge, and you see the corresponding value is 4.3, and for the wall temperature you have 3.6. Can you explain why the two cases give the same value?
T by dx is linearly varying at wall, so that would be same as T
Correct.
wall as linear.
Correct, exactly. So when you say Q wall is constant, in the fully developed case we have shown that the wall temperature varies linearly. Okay, so therefore it should approach the first case where your wall temperature is varying linearly throughout. Okay, so therefore the two Nusselt numbers will have to be the same in the completely fully developed region. Okay, so I think this brings to conclusion all our analytical solutions as far as the internal flow is concerned, and the last part today, which with which I would like to conclude the analytical solutions, will be the region 1, that is simultaneous developing or simultaneous entry length. So this is your region in the duct where your hydrodynamic boundary layer is developing, your thermal boundary layer is also developing. Okay, so this is your region 1. Okay, where both are developing. So that's why it's called simultaneously developing or simultaneous entry length. Now this is a really tough problem. Okay, so you cannot make any assumption to the velocity profiles. So the only solution to this is to solve the momentum equations and get the velocity profile simultaneously, and the velocity profile will not be a constant, it will also be changing with respect to x. Okay, this is a very difficult problem, and therefore if you want to solve the complete equations, so you have to solve the complete Navier-Stokes equations. Now there are some approximations made to the solution if you say for a circular tube with axisymmetric assumption, okay, so that you neglect your variation with respect to the theta direction, so that is your axisymmetric assumption, you can write your momentum equation in the axial direction, that is rho u du by dx plus rho v r into du by dr will be equal to minus dp by dx plus 1 by r d by dr into r u into du by dr. So this equation which we have written right here, okay, so this assumes that there is no variation of velocity with respect to theta direction, and also the radial momentum is also negligible, okay, so therefore you write only the axial momentum equation neglecting the variation with respect to the theta direction, and this equation is very similar to your boundary layer equation. In fact, this is your boundary layer equation, right? So this is your boundary layer assumption. Remember, in the flat plate case we had the same thing, u du by dx plus v du by dy is equal to, if you have a pressure gradient, you have 1 by rho dp by dx plus nu d square u by dy square. The same way we have constructed the boundary layer equation in the radial coordinate system, okay. So this is an assumption to the actual problem, because what you are doing here, you are neglecting d square u by dx square, okay, so that could be important, okay, because if you look at the acceleration in the x direction is important, and also the higher order derivative d square u by dx square also becomes important, which you are neglecting here. And also it sometimes, since it is 3 dimensional, you could also have 3 dimensional effects if you have a non-circular cross section, okay, so these are also not taken into account. So in fact, but you can still get some kind of an approximate solution if you solve this equation for the velocity profile, and but this boundary layer assumption is valid only when you have close to the entry length. If you move far away, once the two boundary layers start to merge, then the boundary layer assumption will not be valid anymore, okay. So this is what comes out of it. But there was a person called Langar, by the name Langar. What he did was, he even neglected the effect of radial velocity, that means he neglected this term straight away, okay, the big assumption, and then he took only the axial velocity variation into account with respect to x and r. He solved this equation numerically, and so the resulting equation which he solved was rho u du by dx equal to minus dp by dx 1 by r into d by dr into mu du by dr. So the boundary conditions that he solved at x is equal to 0, u is equal to ui. So you had some inlet velocity which is a constant, okay. So when it approaches the entrance of the tube, you have a inlet velocity which is constant, and corresponding to r equal to r naught, you have u equal to 0, no slip boundary condition, and at r equal to 0 the profile has to be symmetric, du by dr at r equal to 0 has to be 0. Okay, so he solved this numerically. Of course, you cannot find a closed form analytical solution because of all these terms right here, and he got a velocity distribution which was in terms of Bessel functions, Okay, so these are the Bessel function of the 0th order, and this is the second order Bessel function. The first kind, Bessel function of the first kind, 0th order, first kind, second order. Okay, so here gamma is basically some psi into, it's a function of x by d by Reynolds number. Okay, and your eta was r by r naught. So this was his velocity profile. This is also called as Langer velocity profile. So you see now the velocity profile is a function of x by d through the gamma, as well as it's a function of eta. Okay, so this is the approximate profile that Langer got by the numerical solution to this equation, and with the following boundary conditions. Of course, he neglected lot of things here. So he neglected the radial velocity and things like that. So this is not a very good assumption when you go too close to x is equal to 0, because here you have strong radial components of velocity which are entraining. Okay, so this is slightly this is valid in somewhere intermediate, somewhere maybe from here to here. Okay, but nevertheless it's a reasonable assumption. So using this profile, now you can substitute this into the energy equation. So energy equation can also be solved numerically. So of course you have your energy equation as u by um into d theta by dx equal to d square theta by d eta square plus 1 by eta into d theta by d eta. Yeah, there should be a 2 here if I define my x as x by r naught by Peclet number. Okay, so now this u by um you can substitute from the Langer velocity profile. Okay, and once again now your velocity profile is a function of both your x and y, or your zeta and eta. Okay, therefore okay, so I can use the conventional variables which I used before. I will call this as zeta just to avoid confusion. Okay, so this cannot be again analytically solved, because your velocity profile again is not only a function of eta, but it's also a function of zeta. So therefore this again has to be solved numerically with boundary conditions, whether it's constant wall temperature or constant wall flux, and you get the solution for the temperature and of course the final Nusselt number. Okay, so the solution to this equation was numerically done by, it was numerically integrated by case. Okay, for different boundary conditions, and we will find the solution to all of that one by one. Okay, he is the same Case who wrote the book Case and Crawford, so at Stanford University. Okay, so there are a lot of solutions to basic fundamental heat transfer problems in 1950s and 60s, which were done by 50s, 60s, 70s, which were done by Case. And what happened was he found out, of course, solutions, but the person Hausen, okay, so he comes to our rescue. As we saw already that wherever there is a very complicated solution in terms of Bessel functions or Sturm-Liouville eigenfunctions, this fellow Hausen was kind enough to do an empirical curve fitting and then give a more easier solutions in terms of only Graetz number. Okay, so Hausen came and he took the profiles which were obtained by Case, and then he finally cast them into a simpler form for different boundary conditions. Okay, so the first case was the constant wall temperature. So all these were from using the Langer velocity profiles. Okay, so still they are not the most accurate, but reasonable. So the Nusselt number variation was expressed as 3.66 plus 0.104 RE PR by x by d, which is nothing but Graetz number. Okay, so you can write this as directly Graetz number divided by 1 plus 0.016 into Graetz number to the power 0.8, and constant heat flux case so you see the limiting case where your Graetz number goes to 0 for large values of zeta, so it goes to the fully developed. Okay, so 4.36 plus 0.036 into Graetz number divided by 1 plus 0.0011 Graetz number or 0.8, and finally for the he also did for constant temperature difference. Okay, the constant temperature difference is basically defined as T wall minus Tm is constant. Okay, so for this he got 4.36 plus 0.036 Graetz number, 0.1 into Graetz number divided by 1 plus 0.016 Graetz number to the power 0.8. Okay, so constant temperature difference, the simplest profile that you can think of where you can have a constant temperature difference is if you have a linear wall temperature variation. Okay, so that is one case where you can think about this, and finally both the Nusselt numbers go to the same asymptotic limits. So these were the simplified solutions by Hausen, and of course these are correlations which are much easier to work than the exact solutions or the numerical solutions which were obtained using the Langer's velocity profile. So just to summarize, I don't want to now talk too much about how these solutions came, because they are all numerical solutions, and nowadays the more prudent way of doing this is to solve the complete partial differential equation using computational fluid dynamics and directly get the most accurate solution, okay, rather than putting so much of effort into finding the numerical solution to these approximate equations. Okay, so as far as thermally developing profile has with fully hydrodynamically developed profile is concerned, we can get reasonably straightforward solutions analytically, but simultaneously developing profiles are much difficult, and therefore we need to go for numerical solutions. So on a concluding note, I will just summarize whatever solutions we developed analytically. Okay, if you look at the analytical solution to the problems, first is the geometry or the configuration and velocity profile and the corresponding eigenvalue problem, or I will say eigenfunctions. In fact, I can also introduce boundary conditions. So this is for region 2. So hydrodynamically fully developed and thermally developing. So now look at the constant wall temperature, and if you look the case of channel flow, that is in Cartesian coordinate system, and if you assume a slug flow or a plug flow velocity profile, the eigenfunctions will be in terms of sines and cosines. Okay, when it comes to constant wall flux, the same thing, and slug flow. Huh? What is that? What will be the eigenfunction? Still it will be the same. Only thing, you have to go by this approach whatever I described. Break up into two independent solutions and a perturbation. The perturbation solution will still be homogeneous. Homogeneous with a slug flow will be still sines and cosines. Now T wall is constant or Q wall is constant, channel flow, but a parabolic or fully developed velocity profile. What will be the eigenfunction? Huh? What is that? What function? Bessel function. In a Cartesian coordinate system, you don't get a Bessel equation. Okay, and when it comes to T wall is constant or Q wall is constant, but for pipe flow with a circular cross section, okay, I will say circular cross section, if you have slug flow, what will be the eigenfunction? Bessel. Okay, and the same boundary conditions, circular duct, and if you have parabolic fully developed, then it will be Sturm. So please take note of this. So when you solve any kind of problem, whether it is a channel flow or pipe flow, depending on the boundary conditions, depending on the velocity profile, this you may alternate between either of these kind of equations. Okay, so one more last table, and with that so therefore to summarize all the solutions for fully developed case, that is region 3, and thermally fully developed. So this is all for laminar flow till now. Okay, and when Professor Kolar comes, he will start looking at solutions to turbulent flow. So geometry, velocity profile, wall condition, and the corresponding fully developed Nusselt number. Okay, we will start with a parallel plate. With a parabolic profile, and Q wall is constant. The value is 8.23. Parallel plate, parabolic, and T wall is constant, 7.60. Next, circular tube, slug flow, and Q wall, that is 8.0. Circular tube, and then you have slug flow, T wall, that is 5.75. Circular tube but parabolic, and then you have Q wall, you have 4.36. Circular tube, parabolic, T wall 3.66. Similarly for triangular cross section, triangular duct, if you have a parabolic velocity profile, you have Q wall, then you have 3.00, triangular parabolic constant wall temperature, you have 2.35. Okay. So this is the summary of the region 3 results. We have already done circular tube completely, more or less. Okay. And parallel plate is much easier than this, because you will not have any Bessel equation, you will have straightforward ordinary differential equation for which you can find sine and cosine functions. Then you can see the order in which the Nusselt number decreases. So it is the highest for the parallel plate case, and compared to the constant wall temperature, constant wall flux has always a higher value of Nusselt number. Then comes your circular cross section. Okay, your slug flow always has the highest Nusselt number rather than parabolic flow, and your triangular cross section or non-circular cross sections will have lower value of Nusselt numbers. Okay, so this is to summarize all the results. So we will stop here, and tomorrow and on Saturday, the last two classes, we will look at the approximate methods, the integral method to solving the thermally developing region.